question for day 99 is to solve for z for the complex trig equation of sine of z equal to I. So I'll walk you guys through the solution. But first, if you can, try and solve it yourself. So sine of z can be written in exponential form as follows. Sine of z is equal to e to the iz minus e to the minus iz all over 2i, then obviously still equal to I. Now what we're going to do is we're going to take this denominator across. So we have e to the iz minus e to the negative iz equal to 2i squared. And we know I squared is equal to negative 1, so that just becomes negative 2. Now we're going to let e to the iz equal to w. So what we have here is w minus w to the minus 1 equal to negative 2. So now this is also the same as just having 1 over w. So we're going to multiply through by w for each term, and w times w is w squared, minus w over w, which is just 1, is equal to minus 2w. So we bring this minus 2 across, and we get w squared plus 2w minus 1 is equal to 0. So now we have a standard form of a quadratic equation, and we'll solve for w. So it's difficult to factor this in our heads, so we're going to use the quadratic formula. So we have w is equal to minus b, which is 2, plus minus the square root of b squared, which is 2 squared, minus 4 times by a, which is 1, times by c, which is negative 1, all over 2a. And a is just 1, so 2 times 1 is 2. So our w now equals to negative 2 over 2 plus or minus. Now this all simplifies to 4 minus 4 times by minus 1, which just becomes 4 plus 4, which is just 8. So the root of 8 over 2. And we know that the root of 8 is just 2 root 2. So we rewrite this like this. And those 2's cancel. And here we have minus 2 over 2, and those 2's cancel. So now w is equal to minus 1 plus or minus the square root of 2. Okay. So now, from this point, we'll split it up further. We say w is equal to minus 1 plus the root of 2, or w is equal to minus 1 minus the root of 2. And now initially we said that w was equal to e to the iz. So we go back and sub in e to the iz for w. And since we're writing w in a complex exponential form, we'll write minus 1 plus the root of 2 in complex exponential form as well. And maybe an Argand diagram will help for this, where we have our real parts on this axis and our imaginary parts on that axis. So minus 1 plus the root of 2 is going to be greater than 0 because the root of 2 is greater than 1. So root of 2 minus 1, if we just rearrange these, is greater than 0. And since there's no imaginary part here, our answer will be somewhere over there. So to express this in terms of the complex exponential form, we write the modulus, which is the length, the distance from the origin of this point, which is just minus 1 plus root 2. It's already positive, so absolute valuing it doesn't really make a difference, times by e, and now e is raised to the argument. So the argument is simply 0 because this lies on the real axis. So if it was here, then that angle would be the argument, but it's not. It lies on the x-axis, so the angle is 0. So it's e to the 0 plus 2 pi k I, where, now for this is for all of it, k we're going to be using as an element of integers throughout this video. Okay, now The reason why I added 2 pi k is because 2 pi is 360 degrees, but 2 pi is radians. So 360 degrees from this revolution takes us back to the same point. So that makes sense. So we'll go ahead and do the same procedure now for this. So I'll rub that out, and I'll use the same Argand diagram again, writing w as e to the iz. And now we need to write this number as in its complex exponential form. So the modulus is the distance this number lies from the origin, which is the absolute value of itself. In other words, the absolute value of minus 1 minus the root of 2. And the absolute value of that simply makes the whole thing positive by timesing in a negative, and that becomes then 1 plus the root of 2. So that's the modulus, and the argument is going to be up here in the exponent of e. And so, just to mention quickly where this lies on the Argand diagram, this number specifically over here, minus 1 minus the root of 2 is clearly negative, and it has no I in it, so it's not an imaginary number, so there's no imaginary part, so it lies on the real axis, and since it's negative, it won't be on this side, it'll be somewhere on this side, so it'll be somewhere there, and that is 180 degrees, or pi degrees, or not pi degrees, pi radians, from the positive real axis. So we say pi plus 2 pi k I, and once again, k is an element of integers. So I'll get rid of this Argand diagram for now, and we'll continue with our solution. So z, we've said before, is a complex number, so therefore z takes the form of x plus iy. Okay, but now we have z times by I in the exponent here. So we'll multiply through by I, and what we get is iz is equal to xi, and then here we get plus I squared y, and we simply know I squared to be minus 1, so it's just minus y. So now we move along here, and we have then e to the iz is going to be e to the xi minus y equal to minus 1 plus the root of 2 times by e to the 0 plus 2 pi k I, or e, and we write again this for e to the iz, so now we're writing this down here, e to the xi minus y equal to 1 plus the root of 2 e to the pi plus 2 pi k I. Okay, now what we're going to do is we're going to split these exponents up, and what we have is e to the xi times by e to the minus y, which is the rule of exponents, where if we're multiplying two numbers that have the same base, we can add the exponents. So we're simply doing the reverse of that by going there, is equal to minus 1 plus the root of 2 times by e to the 2 pi ki. I've dropped that 0 because 0 plus anything is still itself, or e to the xi times by e to the minus y equals to 1 plus the root of 2 e to the pi plus 2 pi k I. Now remember, this is the modulus, and that's the argument. So that's the modulus in this one, and that's the argument. Alright, so now what we see is we have two parts on each side, an imaginary part and a real part. And also on this on the right hand side, we have a real part again and an imaginary part, and the same for this equation. So if we continue by equating imaginary parts and equating real parts, we'll do as follows. So first we'll equate the imaginary parts on the left equation, which means we're equating e to the xi is equal to e to the 2 pi ki. Now we can get rid of the bases because they're the same, and we have xi equal to 2 pi ki. Divide through by I, and we're simply left with x equal to 2 pi k. Okay, and on the right hand side, for the imaginary part, we have e to the xi equal to e to the pi plus 2 pi k I. Once again, get rid of the bases and divide through by I, and we're left with x is equal to pi plus 2 pi k. Now we do the same for the real part now. So e to the negative y is equal to minus 1 plus the root of 2, because you see we've dealt with that and we've dealt with that, which means we're just left to deal with these two, which are both real. So now we solve for y, and we have minus y is equal to the ln of minus 1 plus the root of 2, and I got that from doing the natural log of both sides, and I divide through by the negative, and I get y equal to minus ln of minus 1 plus the root of 2. And then for this equation, we've dealt with the imaginary parts, so we're going to deal with these two real parts. So we have e to the minus y equal to 1 plus the root of 2, and we solve in the same manner that we solved this, which is by taking the natural log of both sides, and we're left with negative y equal to ln of 1 plus root 2, and we divide through by the negative, and we get y is equal to minus ln of 1 plus root 2. And at this point, we can write our solution. So we have our solution now in terms of x and y, and that's alright, so because we wrote z in terms of x and y over here. So now what we're simply going to do is z is equal to now x plus iy from here. So here's our x, 2 pi k, so we have z is equal to 2 pi k plus iy, and y is that there, so plus I times by minus ln of minus 1 plus root 2, and if we take this negative out, we simply get that, or let's rather write it more neatly like that, or z is equal to, and now again on this right hand side, our z is equal to x plus iy. So x is this, pi plus 2 pi k, and then plus iy. So iy, we substitute in for y this here, and we get minus I times by ln of 1 plus root of 2. And don't forget to write by the final answer, k is an element of integers.